Hi everybody, I am Daniel and welcome to my presentation about downscaling ecosystem-related biodiversity variables in mountain environments using artificial intelligence. Ecosystem extent and change are key essential biodiversity variables to monitor and better understand changes in the ecosystem distribution within mountain environments. Therefore, maps of ecosystem distribution over time are required. And currently, a global map of ecosystem distribution at a spatial resolution of 250 meters for the year 2015 exists. This map is based on the integration of terrain, land cover and climate information. However, the utility of this map for local scale applications is not yet demonstrated due to the lack of a validation and the relatively coarse spatial resolution. Therefore, the aim of this study is to downscale the existing map of mountain ecosystem extent from 250 meters to 30 meters for two study sites in the Central European Alps and the Himalayas. And for this task, we are first downscaling the land cover component via machine learning using existing land cover information and high-resolution remote sensing data. And in a second step, we integrate the downscaled land cover product with high-resolution digital elevation model data and climate data to produce the downscaled ecosystem map. And today in this talk, we focus on the downscaling of the land cover component. So the land cover downscaling is based on an automatic training data generation algorithm, which uses existing global or regional land cover information and the high-resolution, multi-temporal, harmonized Landsat Sentinel dataset to automatically extract training data for each land cover class. These training data are then integrated with digital elevation model data to train two different classification algorithms, a state-of-the-art machine learning and a novel deep learning approach. These algorithms are then used to classify the tile-based Landsat Sentinel time series and then to generate the downscaled land cover product. The land cover downscaling is written in Python and is implemented in the Microsoft Azure Cloud Platform. Now, to efficiently use the cloud resources, the developed machine and deep learning algorithms are heavily optimized to use multiple CPUs and multiple GPUs in parallel. And the final downscaling implementation was developed in an iterative trial and error process, where the produced land cover maps were regularly visually inspected and discussed to further improve the implementation. So for the land cover downscaling, we used the harmonized Landsat Sentinel dataset, where we considered all images during Northern Hemisphere spring and summer with a cloud coverage less than 50%. This led to approximately 40 to 80 images per tile. Now, given these images, we were interested in the processing time and cost of the developed downscaling approach, where we trained both a random forest classifier and also a deep convolutional neural network. So the processing time to classify a tile of the harmonized Landsat Sentinel dataset using the random forest algorithm is around 35 minutes, which translates to a cost of $1.6 per tile. And in comparison, the processing time for the convolutional neural network is around 30 minutes, but the cost is slightly higher at $1.8 per tile. And this can be attributed to using multiple GPUs in parallel, which substantially accelerate model training, but are associated with a higher cost. Now, having observed the processing time and cost per tile, we were interested in how the developed approach scales to large areas. And for this, we applied the land cover downscaling to the area of the entire European Alps, which comprises approximately 40 tiles of the harmonized Landsat Sentinel dataset. And Figure 5 shows the resulting land cover classification and the processing time and cost of the random forest versus the deep convolutional neural network. So as you can see, we are able to classify the land cover of the entire European Alps at 30-meter resolution using automatically generated training data within approximately 1 day of computation time and a cost of around $70 to $80. And currently, we are producing these maps for the years 2015 to 2020 to assess the changes in the land cover and therefore also the changes in mountain ecosystems. Now, since we are currently in the first phase of this project, there are a couple of open points to be addressed. First, the application of the developed downscaling approach to a study site in the Himalayas. Second, the development of a validation strategy for the downscaled land cover maps and the associated consistency of the maps over time. And finally, the integration with the digital elevation model and climate data to produce the final downscaled ecosystem map. Okay, so thanks everybody for listening, and check out our project webpage for more information. Also, feel free to reach out to me in the live chat at this year's ESAS 5 Week. See you there.